here is another image. Looks like a dragon head. So you see,
oh yeah,
it's about to get loose. So most of the time, these structures are very, very stable. They can exist on the sun for extended period of time, days, weeks, and then they lose equilibrium and they erupt. And the mechanism by which they lose equilibrium is subject of my research. So you can imagine it's always good to have handkerchiefs. So you have a bunch of field lines coming from one spot to another. And one thing about sunspots is you don't know what's happening under the photosphere. And what we know is that there is a consistent rotation of sunspots. If I rotate these bunch of field lines slowly over time, I'm increasing the amount of twist of this magnetic field. Okay? And the more I increase the twist, the more compact it becomes, so intensify the magnetic field. And you also produce some currents that flow from one end to another. And if I continue to twist, what's going to happen to the magnetic field? It starts to kink, right? When it kinks, well, it disturbs the balance it has with the overlying field. Now, this structure cannot be stable. Why it cannot be stable? If you imagine this is like a slinky. You have field lines that are highly twisted. Okay? There is a force that acts on the inner edge where the magnetic fields are more closely spaced than on the other edge. So there is an effective force that acts from the center of this circle outward in all directions. So this will tend to expand and fill the entire volume. So one way to keep this in equilibrium is to have magnetic field that goes around and straps it down. That's called strapping field. Okay? And I'll show you a cartoon of that. Here it is. So you have one end of my handkerchief here, another end there, and you have highly twisted field lines. When you look at the field lines on the inside, they are more closely spaced than the field lines on the outside. So that produces an effective force, which we call hoop force, that points from the center of this torus outward. Okay, so you have an outward force that tends to expand this slinky outward. So to hold it down, you need to have another two sources of magnetic field, one here and one on the far side, produce field line that goes above your slinky. And there will be an ampere force pointing downward that in some certain conditions can balance exactly the hoop force pointing outward. Okay, so you can find conditions in which this configuration can be held in equilibrium. Okay, so you need to have, in a sense, four sources: two to produce your highly twisted field, and another two to produce your strapping field. And that's not easy to do. That's not difficult to do in the case of the real sun. So over time, two things can happen. A, you either continue to twist the magnetic field along this slinky, and in a sense what you do is you increase the current, and when you do so, the strength of the hoop force increases over time. Okay? So this structure will then tend to expand a little bit until it finds a new equilibrium and so forth. Or the field that holds it down tends to weaken over time because it's produced by two sunspots, one here and one on the far side, and they tend to decay over time. So the strength of the strapping field can decay over time. And when you do some analytical work, you will find out that there is a certain point in which the equilibrium of this configuration can become unstable. And when it becomes unstable, it's like having a ball on top of a hill. Either way it goes, you go downhill, and this configuration just erupts and gives your coronal mass ejection. Okay? That's the simplest way to explain how you get coronal mass ejections.